Hi, my name is Ivan Markov, and in today's lecture, I'd like to cover a very hot topic in today's world, which is fake news detection. Please note that the lecture will be recorded. Before I dive right in, a disclaimer. It's hard to completely avoid controversy while exploring fake news. So an important note that neither me nor my colleagues, we do not endorse and are not expressing any political affiliation or intent expressed in the provided examples or suggested data sets. Uh, all right. Let's start with some fake news background, as it helps to grasp the scale of the problem. Throughout the history of humanity, there were a lot of examples of what can be considered fake news, as well as many attempts to fight it. It has always been a never-ending war. But with the advancement of technology, the mass media became more and more accessible, and basically now fake news spread through the internet, television, or radio. It can influence hundreds of millions of people. But probably for us, the most important events took place in 2016. Uh, Back at that time, there were US president's elections, and Donald Trump won them. It was a very close win, and of course, there was a fierce battle of election campaigns prior to elections. And of course, as usual, there are tons of made-up political stories circulating on the internet and social media. And yeah, nothing too unusual, you would say. And you would be completely right. Nothing would have happened, to be honest, if not for one particular event. And well, it's not even an event. It was a report by BuzzFeed that they published in the end of 2016. Basically, what BuzzFeed did is that they analyzed Facebook engagements with top 20 most popular real and fake stories, and they made a startling discovery. Prior to elections, there was a steep decline of engagements with real news and increase of engagements of fake news. And it was up to the point that the engagements with fake news, they surpassed those of real news. And of course, when this report was became publicly available, it caused a great dissonance in masses. And yeah, some people may say that the BuzzFeed report became the first game changer in the war against fake news on the internet. Because of that report, in the next several years, Facebook and Twitter, they partnered with multiple independent fact-checking agencies. They even adjusted their newsfeed so that fake news are displayed less often compared to real ones. And they even added warning labels. Yeah, it was a great idea, and actually it helped with the problem, but it also gave birth to a new one. The problem with manually labeling fake news is that it's quite a slow process, I would say. So basically, yeah, in 2017 or 18, the first pursuits of making the fake news detection process automated has actually started. But before we dive right into the fake news detection topic, let's first discuss what we'll be trying to detect. One of the problems with fake news is that they are quite hard to define. Different sources provide different definitions. They're some more reliable, some like fake news definitions. But I personally like this one. It's a definition by Cambridge Dictionary. They state that fake news are false stories that appear to be news, spread on the internet or using other media, usually created to influence political views or as a joke. And although this definition seems like a good one to me, but I don't feel that it fully describes the scale and the diversity of fake news. So we'd probably want to go for describing the dichotomy of fake news. Also, there are different types of dichotomies, but the one I really like is the one containing 7 different types. And yeah, I scaled them in terms of intentionality of doing some harm, basically malicious intentionality. And yeah, let's check them out. We'll start probably with the least harmful one. It's a satire. Basically, those are manipulated or even made up news, but they do no harm because their only intention is to be funny. And yeah, here's a great example from a satirical website that publishes only satirical news. Yeah, that states that Facebook apologizes for giving Mark Zuckerberg a platform. Obviously, it never happened, and yeah, but still a funny one, and yeah, does no harm. The second one is called false connection. Basically, those are the real stories, but presented with a completely misleading title. They are also known as clickbaits. So yeah, here's an example of a completely legitimate New York daily newspaper, which posted this article well, in 2008, quite long ago, but still. The title states that sugar is as addictive as cocaine, heroin, and well, obviously you can probably say that it's true, but yeah, the way they presented the title, complete clickbait. All right. Next one is probably one that is hardest to detect, and it's called the misleading content. Those usually are the news which are based on real events, but the misinterpretation of facts of those events is just terrible. And yeah, here's an example. Basically, there was a law in the United States of America in 2018 that stated that local authorities had to establish strict water budgets. But yeah, you can see how that story was presented. They basically took like some sentences from the law, they combined it in a completely random way and made it look like really terrible. Yeah, you have to shower and do laundry on the same day. It's illegal. Fines. Yeah, made up story, and yeah, quite controversial. All right, next on the list is false context. Basically, it's the idea of combining different completely unconnected sources to make one news article. Yeah, this is here's an example of such case. Basically, some guy with basic Photoshop skills, he took a very old picture which had completely nothing to do with this article or this news. It was like in the early 2000s, and yeah, a very long time ago, and it connected to a very also clickbait title. Basically, the news wasn't that terrible actually, but yeah, this particular meme, it went viral, and across the whole world it was sent to each other. Yeah, a very nice example of that. Nice. Yeah, now to the worst ones, probably. Among the top three, the first one is an imposter content. Basically, those are the news from completely unreliable sources, but presented as reliable. Yeah, this example actually depicts the ABC News website, which is in fact a very nice news agency. With some kind of a completely made-up story about the China Space Lab, which mostly burns up on re-entry in South Pacific. Well, first of all, it never happened. This story is a complete hoax. And secondly, this snapshot of the print screen, it's not from ABC News, but rather from a website with the same interface, but yeah, completely not connected to ABC News in any way. Yeah, next one is a manipulated content. Basically, it's more about Photoshop rather than changing text. Basically, when you take some real content, which is harmless, and transform it in order to look very, very controversial. So here's an example of Vladimir Putin, the president of Russian Federation, grabbing a necktie of Barack Obama, who was a president in the USA back at the time. And yeah, if it actually happened, well, it could easily, I don't know, start a war or something. But luckily, it's just one very funny guy who had nice Photoshop skills, and he actually just used this picture to make a fake news. Yeah. And probably to the worst one, which is actually pretty simple. It's basically a fabricated content, which is completely made up. It has no basis on reality. And probably, if constructed correctly, it's the most influential one. So here is an example that actually, yeah, I suppose the daughter of Hillary Clinton allegedly confirmed that Hillary Clinton ran the national human trafficking. It's actually a story from 2016 election, and it was a complete fake, but a very popular one. All right, so how can a person spot fake news? Basically, there are quite a simple steps you can take. First, you should probably consider the sources or the author. Basically, have you ever heard of them? Are they reliable? Maybe you should check some other posts on that media or from that author. Then you should probably you shouldn't probably make conclusions by reading only the headline. And yeah, you should definitely check out the full text. It helps you detect clickbaits and don't get upset like too early. Then you should definitely check the style, content, mistakes, because, well, basically most of the fake news are written not very professionally. Yeah, also check the citations if any are present, because sometimes fake news, they send you to some completely, well, fake resources, fake laws, fake papers, fake citations. You should also check if some are present. And of course, you should make your decision based on your prior knowledge, based on your intuition, check your biases, and finally, yeah, make a decision whether it's real or fake. Obviously, this example about Zuckerberg is complete hoax. He's alive and well. All right. In fact, what we just described seems like a binary classification problem with two distinct classes. Basically, you have to process some data, which is text, sources, and stuff, and make a decision, basically class 0 or class 1, real or fake. And of course, it would be really great if a fake news detection system could do all the steps that we've described above for us. All right, so what's the problem? Let's build one and finally save the world from fake news and live happily ever after. Well, it turns out that that's not that simple. Let's imagine this following humorous example, basically make a short step back. Let's suppose we have a data scientist. He or she is rather smart and knows a thing or two about maths and statistics. Maybe he even knows some Python. All right. And our hero has really liked the idea to automatically detect fake news. So he or she knows that in order to build a working algorithms, he needs a news dataset to teach it on. As we discussed, we are faced with a binary classification task. So this dataset preferably should contain labels. At this point, our hero can go two different ways to acquire the data. The first way is a hard one. He can try to collect the data himself. In order to do that, he will need to do some very painful procedures. Basically, he needs to build a parser to scrape the news websites, social media. He needs to sort the collected data. He needs to basically store the data somewhere. He needs to hire fact-checking agency in order to label the data. He needs to solve multiple legal issues because, well, scraping is not legal in all countries in the world. And yeah, although the data collected this way will probably turn out to be really great and you'll probably make a great solution, but it's a very time and resource consuming path. So you'll probably have to be backed up by some sufficient funding to do all that. And if not, it's probably a good idea to join some big IT company who's already facing a challenge of fake news detection and has enough resources to tackle it. Or alternatively, our hero can go another way. Basically, he can just might want to travel to the glorious world of the internet and Google reliable labeled datasets there. And sure, he will find several of those. Some are available on Kaggle, some he'll have to Google explicitly. And sure, I'll also provide you with several links to those datasets in the comments to YouTube video. But after some analysis of the existing datasets, our hero will come to a very simple conclusion. Most of the available datasets have a pretty similar and narrow structure. Basically, the datasets provide you with textual information about the news, sometimes combined with some metadata such as an author or a type of the news, which is also usually textual. And then there is a simple label, if the news is fake or real. And here comes the realization. If our hero follows the second path, he'll have to solve the fake news detection task using natural language processing techniques, as it basically is the task of classifying texts. All right, I'm really sorry for the previous part. I promise I'm done playing around. Yeah, let's sum up what that story was about. Basically, we ended up with two completely distinct approaches. Let's call them the proof of concept approach and the business approach. The first one is making use of publicly available datasets, usually containing text versions of news and binary labels. It's a great starting point. Here you can test multiple hypotheses quite fast, compare your results to others, and participate in competitions. Also, you can look for inspirations in various NLP research papers, which is also a great thing. Yeah, obviously, this was the second path in the example of our glorious data scientist. And the second approach, business approach, it involves using real-world data. Here, you'll have to solve multiple subtasks, such as collecting, labeling, processing of the data, in order to build a working solution. Also, although news mostly contain textual information, you'll probably end up with some other data types and will have to carefully include it in the model. In the next parts of the lecture, we'll explore both of those paths. First, we'll figure out how we can build different NLP machine learning algorithms, from the simplest to almost state-of-the-art ones, on clean data sets available on the internet, obviously, and check how they perform on some kind of benchmark competitions or leaderboards. And then we'll see how big IT companies tackle the task of fake news detection in the real world, and see which problems they solve in several examples. All right, let's start with the first one. Yeah, let's get technical. In this part of the lecture, I'll be using the COVID-19 fake news dataset mostly for demonstration purposes. The dataset was a part of a competition conducted by Constraint AI in the end of the previous year. It was a really great competition. There were around 160 or 166 competitors, and the dataset consisted of almost 11,000 tweets, posts, and articles related to COVID-19, which were split almost in half based on whether they are real or fake. And that data set basically contained the following information: the label, the source of the news, and the text. Also, labeling was done manually, so great. I applaud to the labelers. As they also used, of course, fact-checking agencies, but yeah, still a great effort and a great cause. All right. We will start with constructing the baseline, which is the simple machine learning pipeline, which we will later use for comparison with more advanced models. The first step in the data is the data pre-processing. And obviously, the goal is to clean the data and prepare it for feature generation. At this step, we want to exclude all the little informative data, such as emojis, URLs, punctuation, etc. But to be honest, I feel like it's very basic stuff, so let's not spend too much time here. Yeah, basically, we remove the garbage, then we tokenize the sentences. Basically, we split them by words. Then we remove stop words such as the, is, etc. Then we remove contractions, change number to words, blah, blah, blah. Then we finally stem or lematize it, which is basically like it's effectively reducing the dictionary by changing words to their root forms or simply removing the word endings. So basically what we've achieved by doing all this, we've reduced the size of the vocabulary and made the vocabulary more uniform, basically by getting rid of useless information. I listed some Python libraries that you may find very useful for this task. Basically, NLTK inflect contractions are very popular ones, and you probably want to check out the tweet preprocessor library, which is a great also public library, which helps you work with data such as Facebook and Twitter posts. All right, but after we've cleaned the data, we're still working with strings, and we cannot feed strings into the machine learning algorithms because basically they don't know what the string is. So we need some way to transform strings or words into numerical data. And that's our next step in the baseline, which is a feature extraction step. Namely, there are two most common approaches. First one is called bag of words, which is a representation of text that describes the occurrence of words within a document. Let's check how it works on a particular example. Here are two tweets that we carefully pre-processed, so all the words seem a bit funny, but yeah, those are the tweets. Basically, what we are doing when we want to construct bags of words is that we want to calculate the occurrences of a particular word in a particular data sample. So here's an example. We want to calculate the occurrences of word lab, which occurs twice in the tweet 0 and never occurs in the tweet 1. And basically, we assign 2 to a tweet 0 and 0 to tweet 1. Same thing goes for heart, but vice versa, it's in the tweet 1. And for example, the word COVID-19, it exists in both tweets, and that's why we assigned 2 to tweet 1, because there are 2 COVID-19s, and 1 to tweet 0. Basically, by doing so, we've effectively acquired vectors, which are called bag of words, for each data sample, which contain a lot of zeros and basically counts of words which are present in tweets. The second approach is slightly more complicated. It's called term frequency inverse document frequency, or TF-IDF. And here are some scary formulas describing what it does. So TF-IDF is a product of term frequency and inverse document frequency. The term frequency is a fraction, blah, 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 blah. Let's just check how it actually works, because the concept is very simple. Probably the only formula that we really need is that TF-IDF is the product of term frequency and inverse document frequency. Let's check the same tweet and how do we calculate the term frequency. Basically, also quite simple. Term frequency is calculated according to basically, the term frequency is calculated on pairs of terms and particular documents. So, for instance, if we want to calculate the term frequency of word 1 in tweet 0, what we do is we calculate the occurrences, which is 2, and divide it by the total length of a tweet, which is 14, and we find that it's 0.14 something. And basically some simple example confirms that it's true. All right. Inverse document frequency is slightly more complicated. Basically, what we do is for each term, we calculate the amount of documents this term is present in. And the formula is the logarithm with base 10 of the total amount of documents and the amount of documents containing one. As we remember, there is like 2 examples of word 1 in tweet 0 and none in tweet 1. And that's why we get the logarithm of 2 divided by 1, which is 0.301. Yeah, and basically we do this for every single word, and then we multiply it by term frequencies that we've already calculated. And actually that's pretty much it. And the idea behind the TF IDF is that not only it contains the information whether the term is present in one data sample, but also it contains information whether it's present in other data samples. And also, interesting fact, as you may see, for COVID-19, we've actually calculated zeros in terms of TF-IDF. And it's due to the reason that COVID-19 is present in both tweets. And as we remember how we calculated IDF, it's the fraction of total documents and the documents containing it. And the logarithm of 1 is 0. Hence, we get the 0. All right, hope it was pretty clear. Now let's get to the actually machine learning stuff. And while selecting models you would want to train, you probably want to check what data you ended up with. As we just figured out, we get 2 different approaches, but when we apply both bag of words and TF-IDF to the whole dictionary, we are working with around 10,000 different words, as we have 11,000 tweets and 10,000 words, we actually get that the amount of features is almost equal to amount of samples, and that's why we call it high dimensionality. So basically, the data has high dimensionality. Also, another thing to note is that the data is very sparse, and basically what it means that there are a lot of zeros. Recall that both bag of words and TF-IDF, they have non-zero values only on the position of words which are present in the sample. And tweets, for example, they are around like 30 to 35 words on average. So basically, we have a vector of 10,000 length with only 30 non-zero values, which is, basically less than 1% of values which are non-zero. And that's why the data is very sparse. And finally, we already excluded most of the irrelevant words from our dictionary. So probably we wouldn't be able to significantly decrease the amount of features. But even if we could, I don't know, reduce it by half, it would still be very high dimensional. All right, keeping those in mind, I chose several binary classifiers and ordered them in priority of their potential applicability. To train any of them, I highly recommend you use scikit-learn or XGBoost or catboost for boosting methods. But let's quickly go over the top of those models. Let's start with the weakest pair, which are k-nearest neighbors and the decision tree. And the reason I think they are the weakest in terms of our data set, because they both suffer from high dimensionality. Basically, for k and n, the density of the points gets lower and lower, and it's a distance-based method, and distances make less and less sense in higher dimensions. And for decision trees, the root of the problem is the same, although it's to a bit different reasons, namely as the dimensionality of the feature space increases, the number of tree configurations can grow exponentially. So it will probably end up with something insanely large, and it will probably make a very bad splits in terms of data and just poorly performant, I would say. Next, which I call the average pair, those are the logistic regression and gradient boosted decision trees. Basically, the problem with logistic regression is that for sparse data, it can easily overfit, as there are like a lot of suboptimal solutions for its parameter choice problem. But yeah, there are some ways you can try to solve this issue. For instance, you can apply different types of regularization and make the algorithm more stable, and probably it will perform okay. Yeah, and boosting trees are combinations of decision trees, and although a single decision tree, as we just discussed, is quite a weak classifier in terms of sparse and high dimensional data. Gradient boosted decision trees, they make use of very small and quite weak classifiers, and the strength of the algorithm is because it's a combination of weak learners. And basically there are also different types of regularization that you may apply and achieve also quite decent results if you try to do it very precisely. And yeah, my personal favorites in terms of baseline models, those are naive bayes and support vector classifier. The reason why I think the naive bayes can perform rather well in this setting is, well, because it's naive. And it considers features to be independent. It's the core idea behind the algorithm. So to make predictions whether our bag of words ETF idea is like fake, well, I mean vectors from those methods, it shouldn't, well, the method doesn't consider any correlations between features, but rather it just takes them one by one and checks how, well, basically how correlated, how important is this feature to make a decision. And yeah, it's, so if we have like 10,000 features, well, more than enough to make a quite stable prediction using naive bayes. But of course, this limitation, it also, well, basically limits the prediction abilities of the algorithm. So probably with more data, it will not perform much better. And probably our leader, support vector classifier. There are several reasons it works so well in sparse settings. First of all, it relies only on a subset of points to build support vectors. So it doesn't really care about the data / dimensions proportion because, well, it leverages only several data points. And also, if you are familiar with the method, you would know that it also has a regularization term installed basically into it, which together with the uniqueness of the separating hyperplane it's looking for makes it very stable even with quite little data. All right, so let's check how different baseline models perform on the task of fake news detection in the dataset in the competition that we are looking at. Basically, the metric of interest here is F1 score. It's used for most of the classification challenges because, well, it works well with classes that are not evenly split, and basically, well, what it is, it's a harmonic mean of precision and recall. Here is a formula. You can check it out definitely, but yeah, also very basic stuff. So let's not waste too much time here. And check the results. Yeah, for baseline results, I used the paper which actually described the dataset. So it's constructed by organizer. It's called baseline paper in the table. And then I used several papers by the participants, which were in the top 5% of the leaderboard, namely TU Dublin and Gundapu and Mamidi, who were actually in the 5th place in the end. All right, yeah, so to the results. Basically, this table pretty much sums up what I've said before, and the results, they are ranked just as I said. The 3 methods, which are decision tree and gradient boosting decision tree, they performed rather weakly, achieving only like less than 0.9 F1 score. Then the logistic regression with proper regularization performed, well, better and well, significantly better, I would say. Naive bayes performed almost equally to SVM with well, support vector classifier with the basic TF IDF features, so nothing too interesting here. And finally, among the baseline models, Gundapo and Mamedia, they constructed the SVM, which leveraged a weighted TF-IDF. Also, they did some really cool pre-processing, basically achieving the best results across our baseline models, which is 0.96. Yeah, it's a very strong result, which itself can be a nice solution. But let's figure out if we can do it better. And yeah, it's time to get to something more advanced. So far, we've worked with bag of words and TF-IDF methods, which do not work with the semantic meanings of words or with their ordering. Basically, we only take into consideration the presence of words in samples and nothing else. All right, but obviously it would be very cool if we could work with strings of ordered words, basically our tweets and data samples, as with some kind of numerical vector. So probably if we could assign like a vector to a word and feed it into some cool machine learning algorithm, it would probably provide us with better results. And yeah, basically that's actually what word embeddings are for. Word embeddings are real valued vectors which encode the semantic meaning of the words according to its context, basically. Yeah, namely, there are two distinct approaches. First one involves fixed embeddings. What this means is that we assign a vector to each unique word in the vocabulary based on the whole text corpus and don't change it while processing any particular data sample. In this joke example, here's a sentence, basically Will Smith, Will Smith. It contains only two words, distinct words, but it's completely meaningful in terms of English language. All right. If we applied fixed embedding methods, we would probably end up with just Will Smith, because yeah, no content-specific information is present in those methods. And yeah, three of the most popular ones are probably Word2Vec by Google, which was well, arguably the first one, and GLAV and fastText by Stanford and Facebook, respectively. All right, the second approach involves working with context, and basically those are the models. They are considered to be state-of-the-art in the modern NLP. Not these particular ones, but yeah, same to those. And yeah, they are constructed embeddings based on sample context. There are many different models, as I said, but we'll be focusing on the one called BERT, developed by Google, because basically it was like an insane breakthrough in NLP. And if we apply them properly, correctly to our sentence, we'll probably, yeah, process it correctly, and Will Smith. Sorry. All right, let's start with the first ones and use the example of Word2Vec by Google from 2013. First, yeah, a few words about inputs. Inputs are very simple. Basically, we enumerate all the words in our vocabulary, and yeah, basically assign the vectors of zeros and one on the position of its ID. Example, the cat sat on the mat, 6 words, 6 vectors. But the dimension actually is 7, because we usually want to reserve one particular vector for unseen words, and it's usually the first one, actually. All right, Word2Vec comes in 2 different forms. First one is called the continuous bag of words, or CBOW. Basically, the idea here is to predict the target word by its context. So we take several words before the target word, several words after the target word. We use their one-hot encodings, feed it into the algorithm, and we wanted to predict the target word, or actually the one-hot representation of it. And the other one is skipgram, which is basically the opposite of the first one. We take a target word and we try to predict multiple context words, which with which this word is present in the whole text corpus that we have. The model itself is a two-layer neural network. There are two consequent linear layers and the softmax at the end, which scales the output of linear layers to the probabilities. To the probabilities of particular words. Basically, the idea here is to run through your whole text corpus, pick all the possible sequences of words, and train this predictor, which is basically a classifier, until it converges. Yeah, like really simple, and yeah, let's check where actually are the embeddings, because so far we haven't spoken about them. It turns out that embeddings are simply rows of the weight matrices from linear layers. Yeah, for example, this one. Let's consider it and check out how it works. Let's say that we have a vocabulary of size around 10,000, and we wanted to construct the embedding vector word embeddings of a size 300. Basically, what happens is that we take one hot representations, which are 10,000 long, and multiply it by the weight matrix, which has a shape of 10,000 x 300. And basically, yeah, as an output, we get a vector which is of shape 300. Yeah, basically why the rows of weight matrix are the embeddings is well, solely due to simple linear operation, which is a matrix multiplication, vector by matrix. If we multiply a vector which contains only one and all others are 0, we are basically taking the nth row of the matrix we're multiplying with. So basically, if one is on 4th position, then we'll get the 4th row of the weight matrix, and it will be our word embedding, basically. Yeah. All right, let's see how we can train the word2vec model. There is a slight difficulty while we're training it, because although the training network or neural network contains only 2 layers, it's very wide because we have like 10,000 vocabulary, so the very large weight matrices. And if we wanted to train it in a regular fashion, we'll have to calculate gradients, we'll have to try to update pretty much all the values present in the weight matrix, which seems like a bad idea, to be honest. And that's why authors of the method, they came up with 2 distinct approaches to make the training process faster. The first one is called hierarchical softmax. It's a very math-heavy idea, so let's not get too carried with it. Basically, the idea here is to construct a tree of words of the probabilities, and we will predict not the particular probabilities of words, but rather which path we should take on this tree. And yeah, it works. It works rather nicely, especially in the first epochs of training. But probably the first method, which is called negative sampling, is way more useful. Yeah, so also it's easier to understand. Yeah, in this approach, we still calculate probabilities of target output words or context of words, but we compare them not to all other words as we would do in a general training procedure, but to a small random subset of words. Basically, by doing so, we don't have to calculate all the gradients of all words which were like completely irrelevant to the target word, but only calculate like, I don't know, 10, 15, 20, very little amount. And it speeds up the process very fast. And yeah, some cool mathematical theory states that it approximates very nicely the general training process. All right, let's mention some things you need to consider while choosing this method. Basically, you would want to decide, do you want to train it from scratch, or you can use some, yeah, basically, if you are using some unique data set which contains a lot of unique words and probably does not contain a lot of regular words, you probably would want to teach it from scratch because the embeddings will be more representative. But if you are working with some kind of regular texts, such as, I don't know, our tweets, basically the tweets are considered to be like general purpose texts, then you should probably go for a nicely thought on some large corpus of data, Word2Vec, which you can basically download from Python libraries. Then you should probably decide between the skipgram or SIBO. In general, they perform very closely to each other, so it doesn't make a lot of difference, but there are some pros and cons. Basically, SIBO is a bit faster to train, slightly better accuracy for the frequent words, and skipgram works slightly better for rare words. Whether to do any pre-processing or use raw texts, yeah, also another thing to consider. Well, it's completely up to you. Check different methods and see which perform better. And of course, based on the type of your task and based on the size of your vocabulary, you should probably consider changing the dimensionality of the vector embeddings, making bigger for large texts, large vocabularies, smaller for small, and yeah, obviously. And also size of context window, basically, by changing it, you control how much information about the context is installed in each word vector. And also another cool thing you can do with word embeddings, you can basically factorize it, which is done by dimensionality reduction algorithms, and see what are the like connections between your data in some small dimension, like 2D, which I presented you here. All right, that's pretty much covers up all the Word2Vec stuff. Let's like cover in 2 words, which are the second and the third methods, GLOV and fastText. All right, as the name states, global vectors or GLOV, it takes into consideration the global context rather than shallow window approach as we had in Word2Vec. So the input is a co-occurrence matrix of each word and each context of those words from the whole corpus of text. Next difference is that it's count-based instead of predictive, as the algorithm used is a dimensionality reduction method. The idea behind GLOV is that the dot product of a word embedding and its context embeddings are trained to be equal to a logarithm of the number of times the word and context are used together in text samples. Let's just not focus too much on it. It just works and works quite well. The last one, probably the most modern one among those fixed embedding methods, is called fastText. And it's very similar to Word2Vec in terms of the model and the training process. But the core difference that it works on character level n-grams rather than on words. What it means that basically this method, it splits each word into subsequences of letters of length n. Yeah, those are called n-grams, and learns embedding for such n-grams. And then for each word, we simply average those embeddings for its n-grams to get the final word embedding. Why this approach is cool and practically useful is because after splitting the unknown words, which we may encounter in, well, testing the algorithm, we can still get some information because probably we've encountered some of the n-grams present in those words. And yeah, basically that's the core idea behind it. All right, now let's that's time to go a bit deeper. So far, we've managed to transform our tweets into sequences of word embeddings of different lengths. But conventional machine learning algorithms, they don't know how to work with such sequences. And yeah, that's the reason we have to go deeper. So let's explore the concepts of recurrent neural networks. A regular RNN takes as input a sequence of vectors. It processes them one by one while considering, while considering previous states. And the process goes till the last vector, and the last output is basically used for predictions. And in practice, it's good and all, but yeah, it turns out there are some downsides. Basically, it turned out that basic RNNs, they are not very good in terms of keeping the memory. And for instance, if we're facing the task when the prediction that we should make, it highly depends on the inputs that are, for instance, in the start of the sequence of our data sample. Such simple RNN, it will simply forget what it encountered before and make a very terrible prediction in the end based on the completely irrelevant data. So we basically need some way to decide which information to store and which we will dismiss. And one of the most popular solutions to the problem was proposed back in 1997, and it's called LSTM cell. Here's the full diagram of what goes in one cell, but the core idea is relatively simple. What we want is for information to flow freely across all the words we encounter and update it only when we need it, basically. And that's what the cell state is for, which is called C in the diagram. Yeah, let's go step by step through the LSTM cell. Basically, conceptually, LSTM cell consists of 3 blocks, also called gates. The first one is called a forget gate layer. And what it does, it takes as input a new data sample, it takes some previous intermediate output, and decides whether the new input sample is relevant to our task. It's doing it by computing the sigmoid of a linear operation on our input data and produces basically a score from 0 to 1, which is the importance of the new data sample. All right, the next gate is called the input gate layer. It's probably the most important one. Here we decide what information to update and how. Basically, it's also done by leveraging the importance of particular input, how to say it, values from the input vector, and yeah, calculating some kind of an update to a cell state, which is then propagated to the cell state with some importance values. Yeah. And finally, the output gate layer, it decides what do we want to output. Basically, it takes as input the previous intermediate output, the new input, and decides what do we want to output in the next step, this step. Yeah. And yeah, that's pretty much it. This process follows through your whole input sequence, and the output of the last last hidden state, it will be used for further prediction. Yeah, I hope it's clear, at least in some way. Now let's check how it works with the how do we build the LSTM-based classifier. This pipeline is pretty much everything you need to know about the LSTM classifier. So first, you probably want to pre-process your textual data, vectorize text samples, teach word embeddings. We discussed it already. Then you probably want to limit the maximum length of the sequences because yeah, it's basically done for computation purposes. In general, LSTM network can work with any size of a sequence, but yeah, it's not very nice. But in our task, we are working with mostly short or even very short sequences, so it's not the case. Yeah, and finally, you want to construct the LSTM neural network on top of your word embeddings. Yeah, in terms of classifying text, you usually want to do it to make it bidirectional. What this means is that sometimes you want to read the sequence not only from the start to its end, but vice versa as well. Yeah, usually it's just a nice approach to text classification. And finally, you take the outputs of the recurrent cells and basically apply some kind of linear classification layer or several of those to make to solve the classification task. All right, yeah, as we're done with averagely difficult models, I'd like to get to the hardest part. It will wrap up the technical part of the lecture, so please stay strong. So now I'd like to introduce the concept behind the truly groundbreaking NLP neural network, which is called BERT. It was developed by Google AI in 2018. And when they installed BERT in their search engine, they described it as one of the biggest leaps forward in the history of search. At the release, it achieved state-of-the-art results on most of the NLP benchmarks, such as Glue, Squad, or Swag. And one of the reasons it achieved such results was due to the enormous size of the model, as well as the enormous size of the training data used to teach it. BERT, BERT set a trend of making models insanely large, and the price to teach such models is also insane. The most expensive ones go up to $60,000 for a single training process, which is completely insane. You probably don't want to do it at home on your own. Although today pure BERT models, they are not on top of the leaderboards anymore. If you visit the benchmark websites, you'll see that half of the top models have BERT in their names. And the other half actually is usually named by after other Muppets, but that's a funny tradition across data scientists. As you can see, there is an example from the SWOG competition leaderboard, and actually BERT is still in the 5th place, although almost 3 years has passed, or even more. Yeah, cool. All right. Explaining in details how BERT works, may take quite a while. So let's try to cover it like only in the high-level concepts of it. First of all, BERT uses a tokenization strategy called word piece. The vocabulary is initialized with all the individual characters in the language you're working with, English in our case. And then the most frequent and likely combinations of the existing like letter combinations of words, they are iteratively added to each other. Conventional BERT model used the vocabulary of size 30,522 different words or letter combinations represented by vectors of size 768. So basically, each input is a sequence of length n of vectors of size 768, the same as we had in LSTM part. All right. Here's an example of what word piece tokenization looks like. Basically, I chose one of our tweets that we've been working with, and I underlined the elective surgeries because basically those words appear to be quite rare in terms of word piece, and that's why they got split into 4 distinct words. All right. Also, BERT input requires 2 special tokens, which are CLS and SCP. They are basically indicate the end and the start of the sequence. And also, as we'll now see, the algorithm processes words separately. So each embedding is combined with special positional and segment embeddings to let the algorithm understand the ordering of words mostly. So which class the word is in and what is the order in the original sentence. It's a mathematical, basically it's like constructing a timeline algorithmically. Nothing too complicated, but yeah, I don't feel the need to cover it. All right. Next, now to the hardest part. I'll try my best to describe the processes behind the transformer encoder, but I highly suggest you check out Jay Lamar's blog on transformers for a better understanding, and he was very kind to let me use some of the pictures from his blog. Yeah, it's just amazing. Go check it out. All right. First of all, BERT is an encoder part of a transformer, which you can see in the picture. Originally, there were 2 versions of BERT. BERT base, which consisted of 12 stacked encoders, and BERT large, which consisted of 24 stacked encoders. Each encoder is represented by two operations, which are a self-attention block and the feed-forward block. Self-attention is probably the most important and the most difficult block to understand. So let's check how it works on the very simple example of two words, basically thinking machines, and imagine that they are passed into our self-attention block. So what happens? First, we, of course, we apply the word piece tokenization to it, and we get an embedding which contains all the required information. Then for each embedding, we feed each embedding into three completely distinct linear layers, which are basically reduce the dimension and transform the embedding in some way. And we acquire three different vectors, which are called queries, keys, and values. As the next step, let's consider thinking our target value. Target word. Then we take the query of the target word and multiply it, dot product actually, by keys of itself and all other words that we are analyzing, basically thinking and machines. And we get the score, which is a single number. Then we normalize it by dividing it by 8. It's simply for computational purposes. And then we apply softmax on the vector of, that's called divide by 8 in this picture, and get some kind of important score, let's call it like this. So basically, it means how important are all the other words compared to target word in terms of its context, local context. Then we simply take those scores, multiply our value vectors by those scores, and combine them together. Basically, what it does, it combines all the information we want to get from all other words into this word. And then, we simply sum it up and acquire the Z vector, which is later passed to feed-forward layers of the encoder. What I've just described is actually only one block of self-attention. And in each encoder, in case of BERT base, there are 12 such blocks per each encoder, and in BERT large, 16. And basically, those operations are also completely independent. So we get 12 or 16 Z vectors, which we then have to process in some way in order to fit it to the feed-forward network. Also, it's probably important to know that each sublayer in the encoder also has a residual connection around it, and it is followed by a layer normalization step. Let's not get too involved. Basically, it's done in order to make sure that the training process is as stable and as fast as possible. And finally, the output of the last encoder is used in the loss function for training. I know it sounded like a complete mess, but trust me, it works like a charm. So how does training work? BERT is trained while simultaneously learning to predict the masked words by their context and to predict if the proposed pair of sentences are following each other in the text corpus. Usually you don't want to train BERT-like models from scratch unless you're a millionaire or you have several thousands of dollars to spare. So you probably want to take a pre-trained model and fine-tune it for your specific task. It's also called a transfer learning process. Which came as a surprise to me when I first got to know about BERT, is that the fine-tuning process, it actually is quite simple, and it requires little data and just a few epochs to converge, even when we train the whole BERT model, not only like the final classification layers. For the binary classification task, the goal of fine-tuning is for the model to predict the class by the last hidden state of the CLS token, which we added in the beginning of each data sample, and basically that's why it's there. We can either train it all together and predict classes and probably get very nice results. Or alternatively, you can simply run all your text samples through BERT without training it, and simply take all the final embeddings which it produces and work with them in any way you want. For instance, feeding it into recurrent neural network or convolutional neural network in order to make predictions. Also an important thing to know that right now it's so simple to acquire the pre-learned transformers with different architectures, and I highly suggest you use the Python library called transformers. It contains thousands of those, and yeah, very, very simple, and it supports both PyTorch and TensorFlow. All right, let's check how the models performed in the COVID-19 fake news task. Here's a table of all algorithms which we described before. As suggested, the LSTM combined with fastText embeddings performed slightly better than the best baseline model. Basically, it's 0.97 compared to 0.96, but yeah, very slightly. Then there were several teams who explored different BERT and BERT-like architectures. And yeah, the guys from the 5th place, they managed to achieve a 0.98 F1 score, which is like a really nice surprise. And yeah. And finally, to the winners. And the winner of the competition was the team called G2TMN. Basically, they're from Russian city called Tyumen. Yeah, and how they won the competition? They used a pre-trained BERT model, which was pre-trained on a very large corpus on tweets. Yeah, very recent publicly available transformer. And yeah, it solely managed to achieve quite good results, like 0.98. But as well, they used the ensemble of 5 different CT BERTs, basically with a bit different settings and a bit different, different random seeds. And yeah, the winning metric was 0.9869. Yeah, that was the first place. Also, highly suggest check out the papers by those guys. There are multiple very interesting experiments that you probably find helpful in terms of solving the fake news task. All right, the final ranking pretty much sums up everything we've explored, we've learned so far in this section. And probably I'd like to wrap up the technical part at this point and yeah, get back to the cruel real world with terrible real world data and insanely difficult real world problems. Within the last part of the lecture, I'd like to introduce several fake news detection solutions from big IT companies and as well as the challenges they are facing while solving this task. The first real world problem I'd like to cover is basically a lack of large labeled data sets, and yeah, especially for recently emerged news topics. Basically, what's the problem is that general purpose fake news detection algorithms, they don't work very well with new fake news types, and the problem evolves constantly. People find more and more topics to spread fake news about, and probably even formats of fake news change. And probably what you want to do is to teach your algorithm all the time. It's called continuous learning. You want to feed the new samples to it, the recent ones, in order for it to perform well on new new fake news types. But as I mentioned before, labeling of fake news can be quite a slow process, and like this, you might miss a lot of viral fake news, which is actually a crucial thing for a fake news detection system to have. All right, so Microsoft, together with Arizona State University, they proposed a unique and very cool solution to this problem, which is called multiple sources of weak social supervision. Basically, what they did is they proposed the concept of weak labels. So they considered the situation when they have quite a very little cleanly labeled data samples and a lot of unlabeled, unseen data samples. They applied some heuristic approaches in order to propose weak labels to unseen data samples. Basically, it's done by analyzing social interactions on media, reactions of people, how controversial they are, and well, some heuristics, right? Yeah, like this, they managed to label unseen data points, whether they are real or fake. But there is a problem of training classifier on such weak labels is because basically you want the classifier to take more attention to the cleanly labeled data sets rather than data points, rather than weakly labeled ones, because yeah, weak labels, they are actually, well, not 100% true, I would say. It's not ground truth at any point. So what Microsoft did, they invented a classifier which included the how to say it, which consisted of a classifier and a label weighting network, or LWN. And the purpose of this second label weighting network is only to measure the credibility of the weak labels, so that classifier would yeah, would take more attention with the clean labels and yeah, rank all the others compared to their weights. Yeah, and basically then they taught several deep classifiers. They actually used one was a convolutional neural network, and the other one was a usual BERT that we described. And yeah, they managed to increase the accuracy of prediction, well, the metrics of prediction, by quite a significant margin, which is, I don't know, I really liked this particular example. All right, the second example that I'd like to discuss, and the second problem is basically, well, we all are probably using social media, and we've seen that news are sometimes presented not in the textual forms, but they can be presented as memes, as photos, as photoshopped photos. And yeah, although the text is still the most crucial part of the fake news, there are still some cases when you want to consider the image part of the news. And yeah, as I said, they vary very much. Here's a great example from Facebook AI blog post, which basically 4 completely different versions of completely same fake news. So what Facebook announced not so long ago, less than half a year, was a very new, very cool fake news detection system. It's more like a pipeline rather than an algorithm, which is called the SimSearch.net++. They haven't provided the paper on it, so all of my research is based on their blog posts, but they still managed to explain quite well how does the system work. So basically, the independent fact checkers, they take very new data sets of potentially fake news. They label some of them, then they feed it into the system, and the system aggregates similar posts using image and textual data from those labeled, basically memes or images. All right. Yeah, and it's all fed into a fusion encoder. We don't know yet how it works, but yeah, the concept is clear. It produces basically similarity score, or it actually ranks new unseen images according to the how likely they will be fake. And it's not used as a labeling system yet, but it's used in order to speed up the process of labeling fake news, because the fact checkers, they are able to focus more on like highly suspicious examples, and not to waste their time checking real news just in weird forms. All right. Yeah, and probably the last example which I wanted to speak about. Basically, we we haven't covered what Twitter uses in terms of automatic fake news detection. Well, probably that's because they haven't announced anything yet. But we know that 2 years ago they acquired a very cool startup called Fabula AI, which specialized in a very interesting domain of deep learning called geometric deep learning. In this domain, models they have to face very weird inputs. Basically, it can be graphs, it can be some kind of network, it can be non-Euclidean space graphs. Yeah, just a complex stuff, which is usually used in conventional maths and produces like a very cool and very difficult theorems. But yeah, so right now it's also a very promising field of machine learning. So basically, what Fabula AI did, they analyzed the ways tweets are spread across Twitter, tweets containing the similar information, and they found out that the tweets containing fake news, they spread in a completely different manner compared to real ones. And here is an actually 3D projection of the different types of spreadings of the news that they presented in their article. Yeah, basically what this algorithm, what this approach does, it completely solves the task of early stage fake news detection, because you don't even need labels. If you manage to train this algorithm well enough, then it will probably just detect fake news by the way they are spread, and it will never even look at the content. Yeah, and it's very cool. But I wouldn't. I don't believe that it can work as a solo-standard solution. So probably all the ideas that I described in this part, they are probably better be combined in one very cool algorithm. Yeah, but usually it's all about. Well, it's not. It doesn't work as easily in real world. Yeah. That's pretty much it that I wanted to cover. Thank you very much for your attention. I hope you enjoyed the lecture, because I was really eager to speak about this topic.